Okay, so good morning. Okay, so for the lecture material, the topic on the analog interfacing is not covered. So it's not tested, it's not covered. All right, and the reason why I provide that material is so that, okay, I provide the material so that in the future, if you want to use this board for some other project, okay, that involves analog sensor or anything, you have that material to help you set up the block, okay, and use it for analog operations, okay. But in our project, we're not going to be dealing with any analog interface, all right. So I just give it to you as reference. It's not tested, it's just for your reference only. Okay, so there are two more topics, all right, on the hardware side, okay, before we move on to the OS. Okay, so the two topics are today, timer peripherals, and next week on the UART or serial interface. All right, and with that, basically what happens is for today, we are learning the timer module because we need to apply the PWM, okay, for our motor control. Okay, and next week for the serial interface, we will be able to establish the proper connection between the KL25Z board and the ESP32. Okay, so next week lecture, I will show you a full demo, okay, of how everything connects up together. Okay, and then I'll also upload the material for the ESP32. All right, so you can sort of get started with it and see how to integrate the ESP32 module inside. All right, so again, as per the announcement, this Friday is half day, okay, for CNY. Okay, so those of you who are affected by the lab, all right, just collect the push button switch, okay, and the wires all right, and you can do it on your own. Next week, I will issue you additional KL25Z board. Okay, so each team will get an additional board. All right, so it will help you to sort of spread out the work, okay, and share the board. All right, so please take care of the boards given to you, all right, and use it wisely. Okay, so for timer peripherals. Okay, so the KL25Z has quite a lot of timer blocks, all right, and we are going to look at some of the important ones, all right. So of course, the periodic interrupt timer and the timer module, these are the two main ones we're looking at. Then there's a low power timer block, all right, if you want to operate in very low power mode. Also, there is a real time clock or RTC. Okay, so what is a RTC? RTC is basically a specialized hardware that keeps track of time. Okay, so if you take your handphone or your laptop or whatever, okay, and you shut it down. All right, if you shut down your handphone, all right, if you power it up again 1 week later, it will still show you the correct date and time, correct? Okay, even though it was actually shut down. All right, how does it do that? Because it makes use of a RTC block. Okay, so the RTC block could be a separate standalone chip by itself. They also have that, or if it's already integrated with your controller, then you just draw a very, very small amount of power from your battery source to keep this clock running. Okay, so the next time you boot up, you know how much time has elapsed, so you can update the correct time. Okay, so that is one of the uses of the real-time clock. Okay, and the SysTick is basically the timer that will actually be used by the OS. Okay, so later when we come to the OS part, we will see that everything is in ticks. Okay, so how many ticks some event happens and so on. So this SysTick is part of the timer block which the OS uses. Okay, so let's have an overview of timer block. So in general, so again the poll is always active, and the same link as before. So if you have any questions, you can put in the poll. All right, and then I can answer along the way. Okay, so let's look at the general overview of the timer block. Okay, so we know that in general, timer or counter. So the reason why they say timer or counter is depends on how you want to use it. If I want to have a periodic track of events, then I can use a clock, which could be internal or external clock. Okay, if I want to count events, okay, so if for example I have a conveyor belt, okay, and items are going by, then I can put some sensor here, correct? Okay, and then say that, okay, whenever the sensor is blocked, then there's an item, correct? And that can send a trigger, correct? That can send a trigger, okay, to the microcontroller to keep track of the count. Okay, so that is one way of using the event, okay, using the counter block as the event. If I want it periodic, it's a clock based. Okay, so many years ago, the bus service, SBS bus used to have this, double decker, right? So many times when we go up, then we realize there's no seat, correct? So they implemented this system where they have a sensor and then they'll have a display of how many seats are available. Okay, I'm not sure they still have that because it was a total failure. Okay, every time the number doesn't make sense with the people on top. Okay, so again, it could be because people anyhow move the leg there, play with the sensor, correct? Or sometimes one leg pass, then two leg pass. All right, so it is sometimes not easy for a practical solution. Okay, so it depends on how you want to use it. Okay, so that is the general idea of events or clock-based block. All right, and you can usually say you want to count up, count down, the source, and so on. Okay, so let's look at specifically, okay, for the PIT block. Okay, so this PIT block is a block within the microcontroller, and basically what it does is I can put in a TSV, which is a timer start value. Okay, when I put in a timer start value, what it will do is it will just start to count down. Okay, it will count down until it hits 0. Okay, and then when it reloads, okay, when it hits 0, when it reloads again, it will generate a interrupt. Okay, so it's a very simple block, nothing fancy. Okay, you just put a start value and then it will just start the countdown. When it hits 0, I generate an interrupt and then I can use the interrupt, okay, to or the interrupt service routine to carry out some action. Alright, so it is a straightforward block. Okay, so there's nothing much to discuss about it. It is a simple down counter and then it generates an interrupt. Okay, so the module that we are more interested in is the PWM module. Okay, what we call the timer PWM module or TPM. Alright, so let's look at this timer PWM module. Okay, this timer PWM module, okay, has several parts to it, so we're going to understand how everything comes together. Alright, so this is the main part where we configure the factors of the clock. Okay, the prescale value, the clock source, and so on. Alright, and after that, we have all the individual channels here. Okay, so how many timers or PWM module do I have? How many channels do I have? Okay, so total I have 3 modules. Okay, 0, 1, and 2. And each of these modules has 6 channels. Okay, so technically I should be able to, if I use all of them, I can have 18 PWM. Okay, that is again, you have to be mindful that when I say 18 PWM is 18 PWM on the actual microcontroller. But that doesn't mean 18 PWM on the board. Correct? So you have to remember the board has some limitation, correct? Because when they design the board, they already decide which pin to bring out, okay, which pin to reserve for certain functions and so on. Okay, so you may not have physical access to all the PWM pins on the board. Okay, but if I just use a microcontroller, yes, I have access to all 18 PWM. Alright, so let's understand this block, okay, step by step. Then we see how to program it later on. Okay, so the first thing is the main clock, the timer configuration. Alright, so we have a clock here. Okay, so I can use this CMOD, okay, bits in a register to decide whether I want to use an internal clock or external clock. Okay, so I can clock it internally, which is my 48 megahertz or 20 point something megahertz. Okay, I can use that internal clock, or if I want some other specific frequency, I can use the external clock. Okay, in our case, we will use the internal clock since it's already available for us. Okay, and I can also do a prescaler. So these are quite similar to things you have done before in your Arduino board. Okay, so you have a clock selection, you have a prescaler up 1 to 8. Then I have some bits here to determine whether I want to count up or count down. So I will configure those bits later on. And then there is also a mod value, alright, to determine when I will reset the timer and start over. Okay, so there are 2 modes of counting. One is called up counting, where I count all the way from 0 all the way to what we call the mod value. Okay, once I hit the mod value, I will go back to 0 and start again. Okay, so that is up counting. The other one is the up-down counting. So in up-down counting, I start with 0, go to mod value, and then I count down. Okay, and then I start over again. Okay, so there are different types of counting, which will also translate to different types of PWM signal that we can generate. All right, and whenever I overflow from the top value down to reset, okay, I will go to or be able to say that I generate an interrupt, okay, depending on how I configure it. All right, so whenever the overflow has been registered, I will set the flag. Okay, so this is the idea of flag. So every microcontroller is always this concept of a flag. So the concept of flag means it indicates that something has happened. All right, and the flag is generally tied to an interrupt enable. Okay, which means that if I enable the interrupt and the flag is set, then I say I automatically jump to the ISR. Okay, so that is how all microcontrollers are programmed. You have an interrupt enable and you have a flag. Okay, so in terms of counting, all right, if I want to count external events, all right, so if I want to count external events, then I can say CMOD is 10. Okay, but again, we are not using this mode of operation. All right, in our case, we're using internal clock. Again, the timer overflow is set when I go to the top value and I roll over. Okay, and if I set the interrupt enable, okay, and this flag is set, then I will generate an interrupt. Okay, so you will see that everywhere you will always have this idea of a AND gate. And this AND gate is a hardware block. Okay, and as long as the interrupt enable is set and the flag is also set, okay, then the interrupt is generated, which means I will jump to the ISR. Okay, so in terms of count mode, okay, like we said just now, there are two modes. One is I count up. Okay, I keep counting up, and when I reach the top, okay, when I reach the top and I overflow. So if my mod value is 4. So once I hit 4, at the next clock I will overflow, which means I will reset back to 0. Okay, so when I reset back to 0, then I will trigger the interrupt. Okay, so when mod is 4, that means I count from 0, 1, 2, 3, 4, and when I go to 0, then the interrupt is triggered, correct? Okay, so it's considered as the first 5 count, 0 to 4. Okay, so it's considered 5 clocks, then the interrupt is triggered. Okay, the overflow flag is set. Okay, and if I have enabled the interrupt, then I will jump to the interrupt service routine. Okay, so this is one way of generating a periodic interrupt. Okay, so this is similar, okay, or similar concept to the PIT just now, correct? Only the PIT is counting down. Correct, PIT count down and then reset back to the start value. Okay, this one is you start from 0 and then you count up. Okay, once you have a match, you overflow and trigger the interrupt. Okay, in the other mode of operation is where we count up and we count down. Alright, so when you count up and count down, what happens is I first count up. Okay, then when I reach the mod value, I set the TOF bit. Okay, at the end of that clock. Okay, and then what happens from 4? So in this case, again, the mod value is 4. So after I hit 4, the next clock I count down. Okay, so when I switch over from the top to counting down is where the overflow flag bit is set. Okay, so effectively the periodic interval between each time I set the bit is 2 times of mod. Okay, it's 2 times of mod. Why? Because I count from the top value for the first time I generate, I have to count down again and go up again, correct? So it is 2 times the mod value, okay, based on the periodic interval of the timer block. Okay, so these are 2 different modes of operation. So all these are what you call options that you have if I want to use the timer block for any other application that I want. All right. So these are the general modes of operation. Now the flag that we are going to set or we're going to check for is, one is the timer overflow flag. Okay, that is if I want to hit a match and overflow. All right. And at the same time, I can also link it to any particular channel, okay, which we will look at in a while. Okay, so this channel flags depends on what is the mode of operation. Okay, so what are the mode of operation that I can use? Okay, so we saw the two modes of counting, which is up count, then I overflow. Then the other one is up count and down count, and then I have the interrupts. Okay, so there are different modes of operation. One is called input capture. Okay, the other is output compare. All right, and then there is the pulse width. Okay, so when do I use input capture or output compare? Again, depends on the hardware you're dealing with. Okay, so for example, if I want to make a certain pulse, okay, of a specific width or specific delay, okay, then I can use a output compare mode. Okay, if I want to have an event and then wait for some measurement to know when the next event has happened, all right, so to measure some time delay. Okay, so measure some time delay, then I use input capture mode. Okay, so in the past, when we had two different challenges, so one was the remote control, the other was using a ultrasonic sensor. Okay, so the students had to use the input capture mode. Okay, so the ultrasonic pulse, if you remember, you send out on pulse and you wait for the return, correct? Okay, so the students have to figure out how to use input capture mode to measure the pulse width. When you use Arduino, no problem, right? Just one line of code. You just measure using one line of code. Then when it comes to here, everybody don't know what to do already. Okay, so you struggle a lot trying to figure out how to make it work. Okay, so these are the two other modes. Okay, but the ones that we are interested in is the PWM, because that gives us the flexibility of motor control. Okay, so there are also other registers here, the TPM register. So all these registers, just take note first. Later when we review the code, okay, I will go through in detail all these registers and all these bits. Okay, so we have these registers and these bits here, which we need to configure based on the type of PWM signal that I want. Okay, so let's have a quick recap of PWM. So what is PWM? PWM is basically a digital signal that gives us an equivalent analog voltage, correct? So in your normal microcontroller, you do not have the ability to generate analog voltage because your 1 and 0 is tied to specific voltage. So 3.3 volt or 0 volt and so on. Okay, so if I want anything in between, I need to have the PWM. All right, so if I say this is 0 volt and this is 5 volt, then if I say 50% means it is halfway, so it's 2.5 volt and so on. Okay, so this general concept we all know. So the main idea is I have the on time over the period, okay, the T on over the period times 100%. Alright, that will be my duty cycle. Okay, and that translates to a equivalent analog voltage, and we use this in cases where I want to control the speed of a motor, the brightness of a LED, and so on. Okay, so these are the general use cases of a PWM module. Okay, so let's look at how we can use the actual channel in our microcontroller to generate the PWM that we want. Okay, so there are two types of PWM signal. One is called edge align, okay, which is what we are going to be using. The other one is what we call the phase align or phase correct PWM. Okay, so in edge align mode, okay, in edge align mode, basically what is happening is, okay, we are going to configure two values. One is called the mod value, the other is called the CNV value or the compare value. Okay, and what does each of these do for us? Okay, the mod value, okay, determines the period. Okay, so when I set a particular mod value, my timer will count from 0 all the way to the mod value and then reset. Okay, again it will start from 0, count away to the mod value and reset. So it basically determines the entire period of the timer. Okay, so that is the first parameter we will set. Okay, so the mod determines the periodic interval. All right. Now the next value is the CNV, or the compare value. All right, and what does the CNV determine? It determines the duty cycle. Okay, it determines duty cycle. So if I put a CNV value, whatever value that I put in, okay, when my timer is counting up, at some point of time, it will match the CNV. Okay, so when it matches the CNV, it will trigger a change in the output. Okay, so there are two ways of generating the output. Either we call it high true pulses or low true pulses. Okay, so if I say high true pulses, what does it mean? That means when my counter is counting up, my pulse is high. Okay, when I'm counting up, it is high. Then when the match happens, I switch to low. Okay, so when the match happens, that means when CNV, okay, value is matching with the timer value. Okay, so when CNV match with my timer value, alright, then I toggle. Okay, and I toggle for how long? Until the mod value is hit. Okay, when the mod value is hit, I go back again to the high state. Okay, because I'm going to count up again, correct? Okay, because the mod value flip over means I'm going to count up again. And since it is high true pulses, that means when I'm counting high, counting up, okay, the pulses are high. Then when the match happens, I switch to low until the counter overflow. Okay, so that is basically the edge-aligned PWM, okay, which is also what you're going to be doing for the lab. Okay, so later we'll go through the lab, but this is basically what you will do. Okay, so in order for me to generate this, we need to understand the registers involved, the bits involved, and so on. Okay, so there are some bits here, MSB, MSA, ELSB, ELSA, okay, which we will look at later. But by configuring all these bits in the register, we will be able to generate the correct PWM that we want. Okay, so that is TPM channel for PWM mode. Okay, so the other mode is what we call the center align, also known as phase correct PWM. Okay, so in the center align, we are basically using the counter in the other mode, which is up-down mode. Okay, in edge align, it's only up counting. So I count all the way up to the mod value, then I reset. Count up, I reset. Okay, in this case, we are doing the up-down mode, which means I will count up first to the mod value, and then I will count down. Okay, so in this case, what is happening is everything is double. My entire period is 2 times the mod value. My pulse width is 2 times the CNV. Okay, so this is another mode of operation, okay, which you can also try if you want, all right? And that also determines on your other bits configuration to determine whether you want high true pulses or low true pulses. Okay, so if you look at it, it is again the same behavior. So if I look at it from here, when I'm counting up, what happened? It is high true pulses, correct? Okay, then when the match happens, I flip. Okay, but since it is counting down, I still maintain the low value until the next match happens, then I toggle back up again. Okay, so whenever the match happens, which is here and here, I will always go to high. Okay, so initially I go high when I'm counting up, and when I'm counting down also I'll go high. Alright, so that is the difference between the center align or phase correct PWM compared to the edge align. Okay, both are acceptable, both will work fine for motor control. Okay, but in the lab we are doing the edge align PWM. Okay, so in terms of the code, okay, what you need to do, what you need to prepare is we have the board, correct, and we have the switch. Okay, so this switch we are not going to use for the lab, all right. So previously we only asked you to solder this connector. Now you also need to solder another connector here, all right? And we're going to use port B0, port B1. Okay, now let's look at the registers involved and the port B and port 1. Huh? So, okay, before we look at all the registers, why did I choose port B0, port B1? Okay, so there are a lot of pins, and we need to think of which timer block we want to use, which channel we want to use, and we need to see where it's mapped to. All right, so let's look at that first. Huh? Okay, so let's look through the data sheet and try to get all this information out. Okay, so the first thing is, let's go to the timer module. Okay, so this is the timer module, correct? So if you look down here, as what we said just now, this is the general overview, correct? So we have the main configuration of the clock over here, and then we have channel 0 to channel N. Okay, so this translates to what? Okay, 3 timers. How do I know got 3 timers? Because if you look at the registers, you have TPM 0, you have TPM 1, and you have TPM 2. Okay, so that's how you know you have 3 timer blocks. And for each of this timer block, you can see that for channel, I have channel 0 to channel 5, C0 to C5. Okay, so that's why we know we have 3 timer blocks, and each timer block has 6 channels. Okay, now what we need to know is, of all these channels, which one are available on the actual board, correct? On the actual board. So we need to look at 2 things. We need to look at the multiplex table, and we need to link it back to the pinout that we have on the board. Alright, so let's go to our multiplex table here. Signal multiplexing. Okay, so this table here is very important, because this table here tells us all the mapping that we have within the controller, and we also need to figure out which one we can use for the board. Alright, so over here, okay, we want to use the timer block. Alright, now, which are the blocks I can use? I can use anything that is available to me, okay, as long as I see that there is a pinout for it. Alright, now in our case, I have used port B0 and port B1. Okay, port B0 and port B1. Okay, and why I use port B0, port B1 is because these two map to timer module 1, channel 0 and channel 1. Okay, so you need to know which port pin map to which timer block and which channel. Okay, can I use anything? Yes, I can use anything as long as it's available. Okay, as long as it's available. Okay, and for you to use. Now the thing that you need to be mindful of again is coming back to the pinout over here. Okay, so over here we know that these are the pins that are brought out for us, correct? Okay, that means if later on you want to use other channels, alright, yes you can. You just need to be careful of, is it brought out to the headers over here? Okay, if it is brought out to the header connectors over here, then no problem. Okay, then I can directly use it, okay, and I can program all the pins that I want. Okay, so that is the important thing here. Now let's look through the code first. Let's look at the code first. Okay, so before we look at the code, let me show you the LED strip. So when you collected the kit, we gave you a small rectangular LED strip. Correct? Have you all tried it? Okay, so it is basically a whole bunch of LEDs connected together, okay, as one strip. Okay, so this one I didn't buy. What happened was about 2-3 years ago. So do you all know in engineering also there's a Makers Lab recently opened? Do you all know? Okay, so recently they opened. So they actually came to our Makers Lab to understand how we set up. Okay, so they wanted to also create a Makers Lab there. Okay, and then what they wanted to do is they needed space, correct? And then there was this very old lab there's a lot of stuff which they say that, okay, we want to clear this lab. Okay, so they send out email to the, not say email, they just inform all the staff that this lab is going to be cleared. So it was macam free for all. So I just go there and grab whatever I can grab. Okay, so in my office still got a lot of things. I grab all still there in boxes. Okay, so one of these things that I grabbed was this LED strip. Okay, so this LED strip, last time they used to use it for a hi-fi module project. You know your old hi-fi, when you tune the equalizer, you can see the LED go up, go down. So this LED strip was used for that. Okay, but now we are going to use it for our project. Okay, so let me show you how to connect the LED strip. Okay, so I create just a okay, so basically one side is all anode, the other side is all cathode. Alright, so you just go and experiment, see which one is which one, try to play around and see which one is which one. Okay, and basically you just connect all the cathode. Okay, so of course, rightfully you connect one resistor for one LED, correct? But we are engineers, we innovate. So I just short all the cathode together, correct? And put one resistor. Okay, so it works, why? Because I only want on one at a time, correct? So it doesn't matter. So I put everything, okay, and then you just connect your GPIO pins there, and then you can create this LED running effect, okay, or whatever effect you want. Okay, so that is how you use the LED strip. So it's very easy. You just figure out which side is positive, which side is negative, and then you connect. But if you don't want to use this, you want to use your individual LED also, it's fine. It's up to you what you want to use. Okay, so let's review the code or the registers first. Okay, so let's do this step by step. Okay, so the first thing that we have is the clock gating. Okay, now what is the clock gating? The clock gating is to always turn on the power, correct? For a particular port that we're going to use. Okay, and in this example, I'm using the port B0 and port B1, correct? Okay, so the first thing I do is I enable the power to the clock. Okay, so that's the first thing I do here. I enable the power to the clock. Alright, now the next thing is I want to configure the mode of operation. So this one, we already have done this a few times, correct? Okay, so the first step we always do is we clear the bits. Okay, so when you say N, this means N the complement means I clear the 3 bits, remember? I clear the 3 bits associated with the mux setting, and then I set the mux value of 3. Okay, so why 3? Okay, why 3 is because over here I'm using port B0 and 1. The timer module is alternate 3, correct? Okay, so again it all comes back to which pin you use. If you use another pin, it could be another alternate function. It could be alternate 4, alternate 5. Okay, so it depends on which pin you use. So since I'm using port B0, port B1, okay, in this case it is alternate 3. Now alternate 3 is the TPM module. Okay, so this same pin can also be used for I2C function. Correct? If I were to use the I2C bus, then it will be alternate 2. Since I'm using the TPM module, it is alternate 3. Okay, so this is to configure mode 3. Okay, and mode 3 is the PWM operation. Okay, now, okay, so the next thing is I want to enable clock gating for timer 1. So every peripheral that you have, there is always some clock that you need to enable. Either you need to enable power or you need to enable clock. Alright? Or sometimes both. So in our case, we need to enable timer. And the timer module, okay, so all the clock gating and power is for the SCGC module or SCGC register. So if I come back here and I search, okay, so under SCGC 6 is the register I use for the timer modules. Okay, so TPM0, TPM1, TPM2, these three modules are the ones that are set aside for enabling power for the timer modules or enabling the clock for the timer modules. Alright, so that is why I need to enable the clock for timer 1. Okay, so this TPM1 mask. So where is this TPM1 mask? Okay, so if you right click, okay, go to definition of this, okay, you will see that the mask here is this value here. Okay, so all these are already defined in the header file. Okay, and what does that relate to? That 0x2, okay, refers to which particular bit? It refers to the bit over here, bit 25. Correct, so it's 0, 0, 0, 2. Alright, and 2 means this is 0, this is 1, correct? Okay, so all these definitions are already given for us, in the header file, so we don't need to sort of redo everything. Okay, so we just make use of the definition in the header file. So in this case, when I do a OR, okay, I am actually setting that bit, correct? Which means I am enabling the clock. Okay, now let's look at this. Select clock for TPM module. Okay, so we need to do a few settings. Okay, so the first setting over here is the selection of the clock. Okay, so if you remember over here, one of the first things that we did is we select the clock. We need to select the clock over here. Okay, which clock we are using. So we are using internal clock, but internal clock also we need to configure some things. Alright, so over here there are settings here, SOPT2. Okay, so let's look at SOPT2. Okay, so this is under the Systems Options Register, and there is a TPM source. Okay, there's a TPM source over here which we need to configure. So under TPM source, alright, we are going to set it to this FLL clock. Okay, so this is basically telling us that we are using the internal clock. Okay, so this is telling us that we are using the internal clock, okay, for our timer module. So the internal clock, as we saw in the lab, we can use the default clock setting, which is 20 something megahertz or 48 megahertz. Okay, depend on what setting you have. Alright, now after that, what we need to do? Okay, this mod value, like we said, is for the period. Why I put this value, later we will look at it. Okay, now before I come to the mod value, let's look at the other settings first. Okay, so let's look at these three settings. Okay, so the SC register, okay, SC register, I'm clearing the CMOD and mask. Okay, so let's look at that. Okay, so let me go to the timer module. Okay, so under SC register, there is the configuration here, which is the CMOD and PS. Okay, what is CMOD and PS? The CMOD is the mode of operation, correct? Whether I'm doing up counting or up and down counting. Okay, so that is the CMOD, alright? And the PS is the prescale value. Okay, so that prescale value again ties in with whatever frequency I'm going to operate my timer module on. Okay, so what are the values I have put here? Okay, I've put in a CMOD value of 1 and a PS value of 7. Okay, so all these are again the built-in macros. So if you go down here, okay, if I go to any of this definition, okay, you can see that what they do is they take whatever X value that is provided and they shift it to the correct position and mask it. Okay, same thing as how they do the mark setting and so on. So they take in a value, they shift it to the correct bit position, and they make sure the correct bit position is updated. Okay, so the macro does everything for us. So when I call this CMOD 1 and PS7, what will happen is I will make sure that I will go to this register and say that this CMOD has a value of 0, 1. Correct? And this PS has a value of 7, 1, 1, 1. Okay? So when CMOD has a value of 0, 1 means I'm doing up counting only. Correct? I'm doing only up counting. Alright? On every LPTM counter clock. So in increments. Okay? And the prescale, okay, is based on the divide by 128. Okay, so I'm setting a prescale of 128 over here. Okay, next is the enabling of the PWM. Okay, so I have port B pin 0 and port B pin 1, okay, both the channel 0 and 1 on the TPM1 module. Okay, now what have I done here? Okay, I have set the ELSB to 1 and MSB to 1. Okay, now let's look at this register. So this is the CSC register. Okay, so this is C0SC means it is channel 0. Okay, this is C1SC means it's channel 1. So I'm using timer 1 block and I'm using 2 channels. Okay, channel 0 and channel 1 over here. Okay, so let's look at this too. Okay, so I'm using timer module 1 and channel 0 and channel 1. Okay, so what I want is I want to operate in edge aligned PWM, correct? And that is the objective I want edge aligned PWM. So for that, I must make sure that the MSBA is 10 and ELSBA is also 10. Okay, so these are the 2 bits that I need to configure for the MSB and ELS. Okay, 10 and 10. So how is that happening here? First I clear, correct? When I do a complement means both of this is 0 and 0. Here also is 0 and 0, correct? Because I end with the complement means I clearing all those bits. Then I only set the B bit, correct? I only set the B bit. So the A bit is still clear, correct? The A bit is still clear. So after I do this, I basically make sure the configuration is 10 and 10. So I first clear the 2 bits, and then I only set the B bit. Okay, so the A bit is still 0. Okay, so that is how I get the edge aligned PWM configuration with the 2 line over here. Okay, so of course here I also do for both the channel 0 and channel 1. Okay, now let's do the last part here first. Okay, now this part here is how do I get this value, this mod value. Okay, so we know that this mod means what? Mod means I start with 0, I'm supposed to count all the way to mod. Okay, and then I reset back. Correct? And this mod determines my period, correct? In edge aligned PWM, mod determines my period. Okay? So this 7,500, what does it mean? Okay? Now this comes back to the 2 settings that we need to configure. Again, you can choose other values, okay, in the lab and try it out. Okay? So in the code that I'm going to show you later, what I've done is I have set the setup clock to 1, which means I'm running at 48 megahertz. Okay, so I'm running my board at 48 megahertz, and as you saw here, I set my prescale value to 7, which means is 1 to 8. Okay, prescale bits of 7 means is dividing by 1 to 8. So when 48 megahertz divided by 1 to 8, this is my actual clock frequency. Okay, so my main clock is 48 megahertz, I divide by 1 to 8, and then my clock is now running at 375 kilohertz. Okay, so this is the clock that is now driving my timer module. Okay, so the basic formula is that, so the clock that I'm using divided by n will give me the frequency that I want. Okay, so this, okay, maybe I should not use n, actually the mod value. Okay, so this is basically the formula that you have. So in my case, it is 375k over whatever mod value I want to get a particular frequency. In this case, I have chosen 50 hertz. Okay, so whatever frequency you want, you can put there. Okay, and that will tell you the mod value that you need to use. Okay, so that is all the settings, all right, to make the timer module operate in edge-aligned PWM mode, all right, at this particular frequency, okay, which is 50 hertz. Okay, so later if when I run the code, I should observe a 50 hertz signal. Okay, okay, not 50 hertz signal. I will generate a overflow every 50 hertz, correct? And since it's edge-aligned PWM, that mod value means it's a period. Okay, so these are all the settings that I need, okay, in order to make sure that my timer module works correctly. Okay, so I think it's a good time. We will stop for a while. We'll take a 10 minutes break. Okay, so take time to absorb this first. Whatever questions you have, you can come down and ask me. All right, later we will go through how this will translate to the actual hardware. Okay, and what you need to do after that. Okay, so I'll just give you a short 10 minutes break. Now it's 10:50. 11 o'clock we'll come back. Okay, and we'll continue. If you have questions, you can come and ask me. Okay, so let's continue. So we're going to go through the demo, okay, understand how the code works, okay, and then we will see the waveform, see the waveform generator, so you understand what is happening. Okay, so in the Makers Lab, there are some scopes. There are some oscilloscopes at the other end, the other side of the lab. So you can use those to check your waveform, all right, to make sure it is the correct signal, okay, before you hook it up to the motor and so on. Okay, so this lab is involving both the motor control, okay, the PWM, as well as the audio generation. Okay, because you can use the same PWM module, okay, running at different frequencies to generate the musical tones, okay, which you need to play some music, correct, while your robot is moving. Okay, so I don't know whether I should share it with you. So the very first time that we did this module, I said everybody will play Baby Shark. So the whole lab was only Baby Shark until everybody got sick of Baby Shark. Okay, so after that I said, okay, enough of Baby Shark. Okay, so you all play your own music. Okay, as long as we hear it as a proper music, okay, which whatever you want to reference, that is fine. Okay, so the PWM module, okay, is also the same module you need to use to play some music, okay, and you can experiment with that after you get it working and you observe the signal. Okay, so before we go on to that, as usual, my life hack. Okay, so there are 4 phases of wisdom which you all must understand. Okay, so this is important for your life. So the first thing is what? Known knowns. Means what? You know what you know, correct? Okay, you know what you know. So if I ask you to write some code, you can do it. You know, create a website, you can do it. Create a mobile app, you can do it. So all these are things that you know how to do. Correct? You know how to do. Okay, so what is the next phase? Known unknowns. Known unknowns means what? You must also know what you do not know, correct? Okay, so if I do not know something, you must say, yeah, I do not know, which means that, okay, I need to go and learn this, I need to pick it up or something. Okay, so you know what you do not know. The third one is what? Unknown knowns. What is unknown knowns? That means you didn't know you knew it. Okay, so for example, okay, somebody asks you to go and play a game of soccer, but you never played before. Then you go and play, I'm quite good at it. Correct? But you never realize that you were good at it. But only when you try, you realize you know. Okay? Now the most dangerous one is what? Unknown unknowns, where you do not know what you do not know. Okay? And this is tricky, correct? You don't know what you don't know. Okay? And why you don't know what you don't know? Because it directly stems from this. They are both linked together. Okay? Why is it linked together? Because when you say you know something, do you really know all the things you need to know? Correct? So that is where your, what you call deep knowledge in something comes in, correct? Eventually, when you graduate, you work somewhere, you will become an expert in something. Correct? Some of you maybe cyber security, some of you maybe in AI, ML, some of you in hardware design, something. Correct? So you will choose some part and then you will focus on it, you will become an expert in that domain. Correct? Which means you will know a lot of things. Okay? That is where sometimes, you think you know a lot of stuff, but then realize along the way that there are also things you do not know. Correct? So the only way to fill this gap is to always have an open mind. Always be prepared to go back to being a beginner. Okay? So even though you know a lot of things, sometimes you must say, I also don't know a lot of things. So I must still learn a lot of stuff. Alright? So you must always have an open mind to say, I still have things I do not know, I must still learn. Okay? So again, you apply this to anything in life. Okay? So to cite, this is not my quotation or my phrase. This was quoted very famously by about 20 years ago, Secretary of State, US Secretary of State, Colin Powell. Okay? Why was it very famous? Because this happened just after the 9/11. Okay, so when 9/11 happened, I still was a student. Correct? So I come to school and everybody is talking about it. I was like, what happened? This was before internet, so there's no internet, nothing. I mean, there's internet, but nobody has mobile phone. connectivity and all this thing. So when I come to campus only, I realized that this thing happened a few hours ago in US, correct? So I go back home, then I switch on the news. Oh, this thing happened. Okay, so at that time, the Secretary of State, Colin Powell, made this because they were about to go to war, correct? So he was talking about this in the war context, what you know, what you do not know about the enemy. But I think it applies to our everyday life as well. Okay, so that aside, so we have a long weekend ahead, correct? Long weekend ahead of celebration. So Happy New Year to all of you. Okay, so it's supposed to be the Wood Dragon, correct? Is it a Wood Dragon? Wood Dragon. It's supposed to be a good year. So let's hope for the best. Okay. So in the meantime, in between all your partying, mahjong, drinking, everything, okay. So you can also spend some time to watch something. Okay. So a few years ago, I watched this show, which I think is a must-watch for anyone in the tech industry or venturing into it. Because along the way, you may have some startup idea. You might want to venture into something. Okay. So if you have watched this, don't tell your friend the story. Let them go and watch. Have you watched this? Okay. Those of you who have watched it, okay, good. If you haven't watched it, go and watch it. It was on Netflix. I don't know whether it's still there. It's a limited series. I think about 7-8 episodes or something like that. So you can binge watch it over the whole holiday. Okay. So it's a must watch. Okay. If you haven't watched it yet, I think it's a very enlightening series to understand how ruthless the world is. Okay, so if you have something that you create or you innovate, you must hold it very close to your heart. Okay, and protect it at all costs until you can make it public. Okay, so it's something that for all of us to watch. Okay, so before that, let's look at I want to show you this ChatGPT. Okay, so before I go to ChatGPT, let's look at copyright first. Now, what is this copyright thing? So all our students are very enterprising. Okay, so a few years ago, what happened? This last year, what? One of our graduates, I won't say which department, okay? One of our graduates, after he graduated, okay, I think he had a lot of free time. So what he did is, he take all our lecture slides from all the modules, zip up everything, and put it up for sale on Carousel. Okay, say, oh, you can learn AI, ML from NES professors, buy these notes. Buy hardware design from this professor, buy this note. So it was brought up to our attention, then it became a legal issue, then asked the student to take down everything, all this stuff. Okay, so, legally you're allowed to use whatever that you have, but you cannot resell it anywhere. Okay, just to be clear, so you cannot take our material and resell it anywhere, but it is for you all. You all are students, correct? So you can use it whatever you like, but you just be careful not to technically resell it anywhere. Okay, so another thing is ChatGPT, correct? Okay, so of course everybody is using AI tools, all right, and it's fine. So let's just try ChatGPT. Maybe you already tried. Give me the C code to control the RGB LED on the KL25Z board using the Keel IDE. Looks very nice, right? Okay, so it gives you a code. Okay, now let's examine it first. So it gives you a delay function. Okay, you a delay function. It does correctly configure the SCGC register. Okay, then it controls the PCR register. Correct, which means the mux function. Correct. Okay, and then it controls the data direction register. Okay, to set it to output, and then to set the LED, it uses the PSOR and PCOR register. Okay, so everything is correct. Everything is correct. Okay, now why am I showing you this? Okay, because we can't stop you all from using it. Alright, everybody uses it. Okay, that is fine. Okay, but don't use this as the starting point. Use this as the ending point. Okay, that means you work on the code, try it out first, get something to work first, and then you go to ChatGPT, see what answer it gives. Okay, then you compare, correct? So maybe ChatGPT can teach you something, correct? Maybe it can show you a coding style which you didn't use before. That you say, hey, if I write my code this way, it's more efficient. Correct? So you're free to use ChatGPT, there's nothing wrong. It is a learning tool. Okay? But use it to enhance your standard. So don't use it as the be-all, end-all and just solve all the problem. Alright? You work on it first, then go to ChatGPT, then see what answer it gives you, and you can compare that result with whatever that you have. Okay? So that is important. Okay, so let's look at the code and the demo. So all this code you have. Now the thing just now we said is we are using this 7500. Okay, why? Because 7500 is supposed to give me a 50 hertz waveform. Okay, so the 50 hertz is the period. Correct, is the period. Now the duty cycle, correct? Duty cycle means how much time I'm high. Correct? So what I'm going to do is, I'm only going to do one thing in my main code, which is to set the COV value. Okay, and the value that I set is hexadecimal EA6, and that is basically 3750, which means it's half of 7500. Okay? So technically, if I run this code, I should get a 50% duty cycle waveform. I should get a 50% duty cycle waveform. Why? Because this EA6 is 3750, which is half of 7500. So 0 to 7500 is my full waveform, the period, and half of it is the COV. That means whenever I match, I will toggle, correct? Okay, then I'll reset, then match, I toggle again. That means I should generate a 50% waveform, 50% duty cycle waveform. Okay, and once you do that in your code, you don't need to do anything else in your while loop or nothing else in your main, because your PWM is fully hardware generated. Okay, once I set up everything in my code and I configure it, what will happen is it will just run by itself. The hardware will just continue to run by itself, and I don't need to do anything else. Okay, so you don't need to update COV again, you don't need to change any settings again. Okay, so when I run this code, what will I observe? Okay, so I have my scope here. Okay, so you can see down here, okay, I'm generating a 50 Hz signal, okay, on my port B0 pin, 50 Hz. Okay, so this is what you observe on the scope. Alright, now what I'm going to do is, I'm also going to, in my code here, you see that I have also enabled channel 1, correct? I have also enabled channel 1 with the exact same settings, which is edge align PWM. Okay, and my mod value is the same, okay, is 7500, which is 50 Hz. But now my C1B value is 0x753. And what is 0x753? That is half of 3750. Okay, that means it's basically 1/4 of my period. Okay, so what I want to show you is, I want to show you that we can generate different PWM signal on different channel at the same time. Okay, it's a single timer block, but I can generate different PWM signal. So let me connect. Okay, so we saw the connection before. It's port B0 and port B1. Okay. Okay, so let me see where is channel 1. I think I was connect the ground. Wait on. I just saw it the other day. Okay, interestingly, I don't see it. Wait, let me check whether my hardware is correct. Okay, let me switch to the other channel and see. Okay, so I think it is an issue with the scope thing. Okay, so if I switch between these two lines, you can see the waveform. So you can see this is 50%, correct? Okay, and the other one is 25%. Okay, so these are both happening concurrently at the same time. Okay, so on one channel you have 50% duty cycle, the other person has 25% duty cycle. All right, now when do you use this, correct? When you want to turn your robot, correct? Okay, when you want to turn, so there's of course two ways of turning. Okay, one is what you call a pivot turn, that means you stop one wheel and you turn the other wheel. Or the other one is differential turning, correct? One is faster than the other. Alright, so if your left wheel is faster, then you turn to the right. If right wheel is faster, you turn to the left. Okay, so it depends on how you want to implement your turn. Okay, so that is basically what you're supposed to do for this timer module lab. Okay, and again, you apply this to the generation of your audio signal as well. Alright, so that is basically the lab. So if you look through the lab manual, okay, so everything is explained here. Okay, so you don't need to do any demo or anything. Alright, so we've given you some frequencies to try out. Okay, some notes. Okay, but you are of course flexible to try anything else. Okay, other notes that you want or other octaves that you like. Okay, to try out and see which frequency you want. Okay, can? Okay, so that is the objective. Alright, and for this you just need to make sure you have soldered the additional header pin. Alright, so next week when you come to the lab, okay, there will be additional boards, additional header pin, and also a new set of batteries. Okay, so I'll issue you, each team will get a new set of batteries as well as one additional board. Alright, for you all to keep, you want to use both the board also can, or you want to keep it as a spare board also can, up to you. Alright, so I think that's all we have for today. So next week's class we will just focus on the last part, which is the serial interface, and then we will look at how everything comes together. Okay, so I'll demo the whole thing, how the app that you create, or the controlling device that you create will talk to the ESP32, and the ESP32 will talk to the KL25Z. Okay, and from there you can control the whole system. So you can, once that is done, then you can go ahead to decide how you want to design the controller. Okay, so the demo or one way is create an app to do it. Okay, in the past people have used PS controller or they create their own controller, up to you. Okay, so it's up to you what mechanism you want to use to control the robot. Okay, I'm just going to show you one way, which is the app. Okay, you want to use other way, it's up to you. Okay, so thank you. Okay, Happy New Year to everybody. Okay, and I will see you all next week. Okay, any questions, you can come down and ask me. Okay.